The universe is the totality of all space, time, matter, and energy that exists. It encompasses everything we can observe, from the smallest subatomic particles to the largest galaxies and beyond. Understanding the nature of the universe has been a fundamental quest for humans throughout history, prompting the development of various scientific, philosophical, and religious theories. In terms of space, the universe is incomprehensibly vast. The observable universe, a sphere with Earth at its center, extends about 46.5 billion light-years in all directions. This vastness poses a challenge for scientists trying to grasp the sheer scale and dimensions of the cosmos. However, it's crucial to note that the observable universe represents only a fraction of the entire universe, and the actual extent remains unknown. The universe might be infinite or possess a shape and size beyond our current understanding. Matter and energy are the building blocks of the universe. The composition of the cosmos includes a diverse array of elements, ranging from simple hydrogen and helium to complex molecules and structures. Dark matter and dark energy, although not yet fully understood, are believed to constitute a significant portion of the universe. These mysterious components exert gravitational influences that shape the large-scale structure of the cosmos. Philosophically, questions about the ultimate nature of the universe and its purpose have intrigued thinkers for centuries. Different cultures and belief systems have proposed diverse cosmologies and creation myths to explain the origin and existence of the cosmos. Modern scientific advancements continue to shape our understanding of the universe, challenging and refining previous theories. The study of the universe involves various scientific disciplines, such as astronomy, astrophysics, and cosmology. Observations made through telescopes, satellites, and other instruments have provided invaluable insights into the nature of distant galaxies, cosmic phenomena, and the evolution of the universe. The cosmic microwave background radiation detected throughout the cosmos offers a snapshot of the universe's early moments and supports the Big Bang theory. The Big Bang theory is a widely accepted cosmological model that describes the origin and evolution of the universe. This theory posits that the universe began as an extremely hot and dense state, rapidly expanding from a singularity approximately 13.8 billion years ago. The term Big Bang was coined by the British scientist Fred Hoyle, who intended it pejoratively, but it gained widespread acceptance. Here's a more detailed breakdown of the key components of the Big Bang theory. The Big Bang theory suggests that the universe started from an incredibly small and hot state known as a singularity. In this singularity, the laws of physics, as we understand them today, break down, making it challenging to describe the conditions at that moment. Around 13 to 8 billion years ago, this singularity underwent a rapid and exponential expansion. This expansion is not like an explosion in space. Instead, it involves the stretching of space itself. As the universe expanded, it cooled down, allowing fundamental particles to form. During the initial moments of the Big Bang, the extreme temperatures prevented the formation of atoms. Instead, the universe consisted of a hot, dense soup of fundamental particles such as quarks, leptons, and gluons. As the universe expanded and cooled further, quarks combined to form protons and neutrons. As the universe continued to expand and cool, protons and neutrons began to combine to form light elements like hydrogen and helium. This process is known as nucleosynthesis and occurred during the first few minutes after the Big Bang. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This transition allowed photons to travel freely through space, creating what is known as the cosmic microwave background. The CMB is a faint glow of radiation that permeates the entire universe and serves as crucial evidence supporting the Big Bang theory. Over millions and billions of years, Gravity played a significant role in the formation of structures in the universe. Small fluctuations in the density of matter led to the formation of galaxies, clusters of galaxies, and large-scale cosmic structures. The Big Bang theory has been extensively supported by various observational evidence, including the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. While the theory successfully explains many aspects of the universe's evolution, questions about the exact nature of the singularity and what happened before the Big Bang remain open and are subjects of ongoing scientific investigation. In general, is the universe eternal, or will it have an end? Various theories have been proposed by scientists over the years about how the universe will end. Here are the more supported of these theories. The heat-death theory, a captivating concept in the realm of theoretical physics and cosmology, delves into the distant future of the universe, contemplating its ultimate fate based on the principles of thermodynamics. At its core, this theory revolves around the second law of thermodynamics, a fundamental principle that dictates the behavior of isolated systems. As we unravel the intricacies of the heat-death theory, a narrative of cosmic evolution and eventual entropy emerges. The second law of thermodynamics, a cornerstone of classical physics, asserts that entropy, a measure of disorder or randomness within a system, tends to increase over time. Applied to the cosmos, this law propels us into a cosmic saga where the universe undergoes a relentless march towards greater disorder and equilibrium. A crucial player in this cosmic drama is the expansion of the universe. Observations and measurements of galaxies receding from one another provide evidence of an expanding cosmos. As the universe stretches, energy gradients diminish and temperature declines. This sets the stage for a scenario where heat, once vibrant in the fiery cores of stars and scattered throughout the cosmic expanse, dissipates into the void. The temperature decrease is a pivotal aspect of the heat-death theory. As the universe expands, it cools down, and the energy within it becomes more evenly distributed. This cooling trend aligns with the broader narrative of the cosmos moving towards a state of maximum entropy, a state where disorder reaches its zenith and any semblance of structure fades into the cosmic background. The concept of maximum entropy is central to the heat-death theory. In this hypothetical future, the universe approaches a point where all matter is uniformly spread and energy gradients are minimized. This equilibrium marks the end of dynamic processes, as there are no longer energy differentials to fuel phenomena like star formation, a stark departure from the vibrant and dynamic universe we currently observe. Galaxies, once gravitationally bound structures, lose their distinct forms as they drift apart. Stars, the celestial furnaces that illuminate the cosmos, eventually exhaust their nuclear fuel, leaving behind dim remnants. With each cosmic eventuality, entropy increases, and the once intricate tapestry of the universe unravels into a state of homogeneity. Considering the vast timescales involved in cosmic evolution, estimating the timeline for the heat death is challenging. The role of dark energy, a mysterious force driving the accelerated expansion of the universe, introduces additional layers of complexity. It becomes apparent that the heat death is a fate measured in trillions of years, a temporal landscape that challenges our capacity to comprehend. The implications of the heat-death theory extend beyond the cosmic canvas to the realm of existential questions. As the universe approaches its equilibrium, the prospect of sustaining life in any recognizable form becomes increasingly untenable. Energy gradients, essential for the processes that underpin life, dwindle, leaving a desolate and frigid cosmos. While the heat-death theory offers a compelling narrative for the fate of our universe, it is crucial to acknowledge the dynamic nature of scientific understanding. Ongoing research, technological advancements, and discoveries may unveil new facets of cosmology, potentially refining or challenging elements of this theoretical framework. In the grand tapestry of cosmic exploration, the heat-death theory stands as a captivating chapter, inviting further inquiry into the profound mysteries that shroud the destiny of our vast and ever-evolving universe. The Big Crunch theory was a cosmological hypothesis suggesting that the expansion of the universe, driven by the force of the initial Big Bang, might eventually slow down and reverse. In this scenario, the gravitational attraction between all matter in the universe would overcome the outward expansion, leading to a contraction of the cosmos. This concept was closely tied to the idea of a closed universe, where the total mass density was sufficient to halt the expansion and bring about a collapse. The fate of the universe, according to the Big Crunch theory, depended on the critical density, a balance between the expansive force of the initial explosion and the gravitational pull of matter. However, as observational data accumulated, particularly from studies of distant supernovae and measurements of cosmic microwave background radiation, the evidence pointed towards an accelerating expansion of the universe. This discovery led to the formulation of the now widely accepted Lambda CDM model, incorporating dark energy as a dominant force responsible for the accelerated expansion. The Big Crunch theory lost prominence as the prevailing model shifted towards an open or flat universe with ongoing expansion. While the idea of a Big Crunch has not been conclusively ruled out, current observational evidence aligns more with a future universe that continues to expand indefinitely. In summary, the Big Crunch theory was a speculative hypothesis about the ultimate fate of the universe, suggesting a contraction phase after the initial expansion. However, modern cosmological models, supported by observational data, favor a different outcome involving perpetual expansion and eventual cooling of the cosmos. The Big Rip theory is a speculative cosmological model that describes the ultimate fate of the universe. Proposed in the early 21st century, the theory suggests that the expansion of the universe will continue to accelerate at an ever-increasing rate, ultimately leading to a scenario where all matter in the universe, including galaxies, stars, planets, and even atoms, is torn apart. The basis for the Big Rip theory lies in the nature of dark energy, a mysterious force thought to be responsible for the accelerated expansion of the universe. Unlike matter and radiation, dark energy does not dilute as the universe expands. Instead, it remains constant or even increases over time. This relentless expansion driven by dark energy becomes more pronounced as the universe evolves. In the Big Rip scenario, the cosmic scale factor, which quantifies the size of the universe, diverges to infinity in a finite time. As the expansion accelerates, it becomes strong enough to overcome gravitational forces holding structures together, starting with galaxy clusters, then galaxies, stars, and eventually even atoms. The tearing apart of cosmic structures occurs in a cascading fashion, ultimately culminating in a cosmic singularity, where the very fabric of space-time is ripped apart. The timeline for the Big Rip is dependent on the properties of dark energy. If dark energy possesses certain extreme characteristics, such as a phantom energy component with a negative equation of state, the Big Rip could occur in the distant future. However, observational constraints from cosmic microwave background radiation, supernovae data, and other cosmological measurements currently suggest that the expansion of the universe is not consistent with a rapid Big Rip. Vacuum decay theory is a speculative concept in theoretical physics that explores the potential instability of the vacuum state in quantum field theory. The vacuum, in this context, refers to the lowest energy state of a quantum field. The theory suggests that our current vacuum might not be the absolute lowest energy state and could undergo a phase transition to a lower energy state. This idea is particularly associated with the Higgs field, which is responsible for giving particles their mass in the standard model of particle physics. According to vacuum decay theory, there is a non-zero probability that the Higgs field could transition to a lower energy state through a process called quantum tunneling. This transition could have profound implications for the fundamental properties of the universe. The The key parameter in this theory is the vacuum decay rate, which determines how likely it is for the transition to occur. If the vacuum decay rate is sufficiently high, the transition could happen, leading to a rapid and catastrophic change in the structure of the vacuum. This hypothetical process is often referred to as a phase transition bubble or false vacuum collapse. One of the notable consequences of vacuum decay is the potential creation of bubbles with different physical laws inside them. These bubbles would expand at nearly the speed of light, and anything within them would experience a drastic change in the fundamental constants of nature. This scenario raises intriguing questions about the fate of our universe and the existence of other regions with different physical properties. It's important to note that vacuum decay theory is highly speculative and has not been experimentally observed or confirmed. The theory involves complex mathematical models and relies on certain assumptions about the properties of the vacuum and the Higgs field. Additionally, the energy scales involved in vacuum decay are beyond our current experimental capabilities to probe directly. While vacuum decay theory adds a fascinating dimension to our understanding of the universe's potential fate, it remains a speculative concept that requires further theoretical and experimental exploration to validate or dismiss its implications. Despite all these theories, we still don't have a clear idea of how the universe will end. As technology and science develop, more realistic theories, perhaps a definitive answer, will emerge. However, it is important to note that the universe is a much more complex concept than we imagined.